Let's take a look at how we can use lasers to understand more about quantum mechanics in atoms and molecules. So one way that we can use lasers is we can use lasers that have a very narrow line width and that are tunable. And lasers, we often think of lasers as having a particular color. For example, a laser pointer, which is technically a laser diode, not a laser, but it has either a red color at 635 nanometers or a green color at about 532 nanometers. And so a laser like that has a very specific wavelength associated with that, and something a little bit fancier than a handheld laser pointer. That line width can be made either extremely narrow, or it can also be made such that there is some tunability to the output wavelength of a particular laser. So one way that we can use a very narrow line width and tunable laser is for precision spectroscopy. So for precision spectroscopy, we're really taking advantage of that narrow line width and tunability to get a spectral resolution that is much, much finer than you could ever get in a traditional spectrometer. And so this precision spectroscopy, most of the time we're thinking about looking at spectroscopy of very small atoms and small molecules. We're probably looking at something in the gas phase where there are no interactions between molecules to give you to broaden the line widths of those quantum mechanical transitions. Probably also looking at very cold temperatures, where again those line widths of atomic and molecular transitions are much sharper. So an example might be we might look at transitions between, say, a ground state and an excited state, and we can, with even a black body radiation source, a light bulb, we can use a spectrometer and resolve the vibrational levels in this vibronic spectroscopy. However, if we wanted to, on top of that, if we had some molecule where we wanted to see both the vibronic and the rotational levels, so we wanted to perform rho vibronic spectroscopy, that might be a case where maybe we want to bring in a tunable narrowband laser. And in general, a lot of the precision spectroscopy and the most accurate things we know about atoms and small molecules come from this type of spectroscopy using very narrow line width lasers in the gas phase at cold temperatures. Another example of where we might use a narrow line width laser, in this case not tunable, but just a single narrow wavelength laser, is in Raman spectroscopy. And we haven't really talked much about Raman spectroscopy, but the way Raman spectroscopy works is you start out in a ground state, and I've drawn a ground state potential energy surface here, and we have two vibrational levels in that ground state. And so Raman spectroscopy tells us about those two vibrational levels, and the way that it does that is we have a narrow band visible laser, so something like a 632.8 nanometer helium neon laser, makes a transition to some high-lying state. And I've just drawn this as a virtual state, i.e. a state that doesn't actually exist. And so we excite it up here, and the molecule spontaneously de-excites. This is actually a scattering process. And it can de-excite down to this V equals 1 vibrational level. So it started out on the V equals 0 level, and it can end up in this V equals 1 level. And so what we measure here in Raman spectroscopy is we actually detect this wavelength of light. And you'll notice that this is energy here. This is a shorter arrow, so this means this is a slightly smaller wavelength of light that's being scattered than the wavelength that's come in. And so if this is, say, 632.8 nanometers coming in, this might be 650 or 670 nanometers in our scattered light. And then the difference in energy between this photon and this photon, so the energy of this 632 and this 670 nanometer photon, that difference in energy gives us our vibrational energy. And so in order to do that, we're going to need a source that has a very well-defined and narrow line width. Now, it turns out it is technically possible to do Raman spectroscopy with a blackbody source. In fact, Lord Raman back 100 years ago, who won the Nobel Prize for this, actually performed Raman spectroscopy using filtered light from the sun. That's sort of an extreme case. Ordinarily, that type of spectroscopy doesn't really work beyond a simple demonstration experiment. That's kind of a heroic experiment. And so this goes from sort of being heroic, can work on a couple of systems, to being a very useful general lab technique when we have a narrow line width excitation laser source. And so we can easily, if we know this wavelength, we can measure this wavelength in a spectrometer, and we can therefore know the energy of our vibrational transition. But this requires that very well-known narrow line width laser to begin with. Finally, another reason that we might use a narrow line width laser is if we want to perform some sort of spectroscopy that requires a lot of power in a narrow frequency range. So even something like a laser pointer doesn't produce really a whole lot of light, but it does produce all of that light in a very narrow frequency range. Even a handheld laser pointer on the side will say something like 635 or maybe 650 nanometers for a red laser pointer. And even for a cheap handheld toy like that, all of that 5 milliwatts, assuming that it's one that follows regulations, all of that power is within a very narrow range around that 635 nanometer region. And so you can get a lot of photon power within a lot of photons all in that narrow frequency range. And so there are a lot of spectroscopies that might require a whole lot of photons all at once that are resonant with a particular quantum mechanical transition. So an example of that in my own research, I do spectroscopy involving very small numbers of molecules or even single molecules. And so there's an instance where I often need a laser source that has a lot of power in the frequency range that I'm looking at. Now, the other sort of extreme that we can go with laser spectroscopy is to go to very short time domains and to get very detailed time domain information about a variety of atomic and molecular processes. So we can do this because lasers can produce extremely short pulses. And I won't go into here how we can produce extremely short pulses from a laser. But if we compare a laser to, say, a light bulb, we can flick a light bulb on and off fairly quickly, maybe a millisecond if we flick that light bulb on and off electronically. But most chemical processes don't happen in this extremely slow time scale of a millisecond. Really, for chemical processes, we want to be many orders of magnitude faster in our time resolution. And so a modern laser can very easily straightforwardly produce pulses that are 100 femtoseconds or shorter. So it's very common to see lasers producing pulses in the, say, 30 to 150 femtosecond regime and getting information about chemical reactions, motions of nuclei, motions of electrons on this 100 femtosecond timescale. So that's 10 to the minus 13 femtoseconds. If we want to look at really fast electronic processes, we can go even shorter, and nowadays it is possible to build a laser that produces pulses shorter than about a femtosecond. However, that's extremely difficult. And we can really already get quite a lot of information out. Most information we can already get out in this 100 femtosecond or so regime. And so how do we get this, once we have a laser that has this pulse of just a little packet of photons all being emitted at the same time, much like you might imagine in a Star Wars movie, how do we actually get time domain information out about a chemical system? And so the way that one way that we can do this is through pump probe spectroscopy. And in pump probe spectroscopy, we have two laser pulses, one that we'll call pump and one that we'll call probe. That first laser pulse, what that does is it initiates some reaction or process. So this might be, let's say, a chemical reaction where that chemical reaction can be initiated by, say, a UV photon. And there are plenty of chemical reactions that can be initiated by a UV photon. That's our pump pulse. And then our second pulse is going to come sometime afterwards. That second laser pulse measures something about the sample. So it might measure, does our molecule still exist? Have we started to form product? Have we started to form some intermediate species? And really this second laser pulse can be any wavelength. It doesn't have to be the same wavelength as our initial pulse. We might have an initial pulse that's UV to initiate a reaction, and then an infrared pulse to learn about the vibrational spectroscopy of that molecule. And if both of these pulses are very short on this sort of 100 femtosecond time scale, then that second laser pulse is going to tell us the current state of the molecular system some time after that pump pulse gets there. And so the time delay between our pump pulse and our probe pulse will give us that dynamical information of how fast do particular processes happen. So how do we get that time domain information out? Well, the way that we can do that is we can actually use the speed of light to our advantage here. So the speed of light can be used to delay the probe pulse relative to the pump pulse, such that the probe pulse can come in and record that spectroscopic information a very small amount of time after our pump pulse. So we know the speed of light is 3 times 10 to the 8th meters per second. And so what we can do is we'll keep that in our minds. We have some laser where we've got a pump and a probe pulse. The way I've drawn this, it kind of indicates that there might even be the same color, but they could be different colors. And we encounter a beam splitter here. This beam splitter splits our pump and our probe pulse. So we're just going to follow our pump pulse this way, and it bounces off a couple of mirrors and goes through our sample, and let's say it initiates some chemical reaction. Our probe pulse comes in and says, hey, have you formed any intermediate yet? Or, hey, have you formed any product yet? And so the probe pulse goes through a sample and hits a detector and tells us whether we still have reactant, whether we formed product, whether we formed intermediate. And so how do we control this timing between pump and probe pulses? What we can do is we can put two mirrors on a movable stage. And so you can see this probe pulse comes in here, bounces off this mirror, comes up and hits this mirror on a stage, and comes back kind of the same direction before going to the sample. Now, if we move these two mirrors back further, this probe pulse has to travel a farther distance. We know it's traveling that farther distance at 3 times 10 to the 8th meters per second. So if we do a little bit of math in our heads, and it travels this extra distance and this extra distance, so up and down in our drawing, then a little bit of unit conversions in our head, a 1 micron delay gives us a delay of 6.66 femtoseconds. And so as long as we can controllably and carefully delay these mirrors on this movable stage, we can record our time-resolved spectrum of, hey, how much reactant do we have? How much intermediate do we have? How much product do we have? At a variety of different time delays, which correspond to a variety of different mirror positions. And so we can record those spectra at, 0 femtoseconds after the pump pulse, 100 femtoseconds after the pump pulse, a picosecond after the pump pulse, a nanosecond after the pump pulse, and sort of really track this chemical reaction in real time. And so this is really just the tip of the iceberg in terms of laser spectroscopy. But this gives you just a tiny taste of the types of questions that we can start to think about